Again, this example should sum up everything we need to know about friction, the fun equation, FBDs, good review of FBDs, and our graph that we were talking about with all the types of friction. Okay, so here's what we want to find. We want to first draw an FBD for each, and then we would like to find force of friction and force applied in each situation. Now notice it doesn't tell us whether it's going to be static or kinetic. We're going to have to figure out, based on the situation, if it's static or kinetic friction. Alright, so we've got our 10 kilogram box. What's the easy force we know right away? Pretty much in everything. Okay, we got mg. So let's draw that on there. And that's going to be 98 newtons. Counteracting that, we've got normal force, or Fn if you want to draw it like that. And it's also 98 newtons. Nothing is pushing up or down on this box. Okay, force applied, 0. Alright, so what's the force of friction? 0. Force of friction is equal to 0 newtons. Now notice this, if we use the fun equation, it would lead us astray. Okay, if we do mu static times normal force, it'll give us a value for the force of friction. Okay, but if we did that and we added it to our free body diagram, then it would mean the box is just going to start sliding. Okay? Alright, so remember, static friction is a lazy force. It will only act if it has something to act against. Okay, force of friction, 0. Alright, also, let's add this in here. F net is 0 newtons. Okay, now we have a force applied. Let's just copy our FBD again. We got mg, we got normal, we got FA equal to 10 newtons. Okay, and we got to figure out what friction's going to do. Here's where we're going to use the fun equation. You always want to check static friction first. So force of static friction is mu static times normal force. Alright, let's plug in some numbers. Mu static is 0.4, and our normal force is 98 because it's just opposite mg. Okay, did somebody punch that in? 39.2. Okay, so that's F static. Alright, now that is always, anytime you do this calculation, that is always static max. Okay, so we're not actually going to get 39.2 newtons. How many newtons are we going to get? Yep. Okay, so F static is only 10 newtons. Because again, if friction decided to act with 39.2, then the box would just move the other way. As the person tried to pull to the right, it would just move left. Okay, which doesn't make sense. So again, lazy force, that comes up a lot. Force static equals 10 newtons. Okay, any questions on that? Okay, what do we got?
So will it start being kinetic friction once the force applied passes 39.2?
Absolutely. It will start being kinetic the instant we pass 39.2. Okay, so the next, these are real easy. Alright, I'm not even going to draw the, let's just draw the FBDs real quick. Changed my mind. Okay, we got mg, we got normal. They haven't changed. Here we've got a force applied of 20, so, and I'm not drawing these proportional to the y forces. Okay, what's the friction going to do here? Without even calculating anything. It's just going to be 20 as well. And it's going to be static. Force static equals 20. Okay, and I'm just using the 39.2. We're still below it. Okay, so force static 20 newtons. Okay. Alright, here we're at 30 newtons, so force static, it's just going to be 38 newtons. We still have not passed our static max. Okay, and F net's 0 for both of these. Okay, now we finally break free of static friction here. Okay, and now that we know that we are over static friction, what's going to happen to the overall friction? It's going to drop because we have entered into kinetic friction, which has got a lower mu. Okay, so let's use the fun equation. Alright, plug in some numbers. This time using 0.3. And a normal of 98. This will give us only 29.4 newtons. Okay, so friction is dropped. We'll label that FK. And let's put it on our FBD as well. We'll draw it shorter than the 40. And this time we're going to have an F net that is not 0. Okay, F net's 0 for this whole thing. The thing's not even moving. Here we're going to get an acceleration. Okay, so let's put F net on here. And we have an imbalance of how many newtons here? Okay, we've got 10.6 newton difference. Okay, and by the way, if we wanted to find the acceleration, it doesn't ask us to do that, but if we needed that, we just divide by the mass. F net equals ma. Okay, remember Newton's second law only applies to F net. So let's put over here acceleration. If we divide that by 10, we get 1.06 meters per second squared. A lot of times we will be asked to do that. Okay, now, do you guys have a little room up here to sketch that graph? Maybe you do it on the back side or something like that. I'm just going to use a little of my space right here. So let's graph what we just did. And this would be the same for any situation like this. Okay, so over here's force of friction. Over here's force applied. And for a while, those are just going to match each other. Okay? In other words, 1 Newton, 1 Newton. 2 newtons, 2 newtons. Okay, so what's the slope of that line? Yep. Slope equals 1. Okay, they match each other. then we're going to get to this point where we break free of static friction. So over here, force static max. That is the maximum friction you're going to get. Okay, and then it drops very sharply. Okay, it drops down. It actually has got a little curve like that as we're breaking free. Okay, we don't really care too much about that, but we'll draw it on there. Mostly we care about the fact that now this force doesn't change. Okay, it stays constant no matter how much force applied you have, no matter how hard you pull on this thing. Go over here. This is Fk. Force kinetic friction, it is constant. Okay, and if you understand all of this stuff right here, you're pretty set on friction. Okay, that's all we really need to know with that for now.